Okay, so a lot of you are probably familiar with what Yara is. You build a rule, it's kind of like a signature, and you can use it to hunt malware. Now, a lot of these rules that you see that are built only using strings. And when you start adding in things like string obfuscations, the strings no longer work. So if you look at malware from uh, 10 years ago, for example, and you look at the same malware today, your Yara rule probably won't work. So basically, I'm going to show you how to build Yara rules that are actually going to last while threat hunting. So just to tell you a little bit about myself, let me get this. Thanks. Okay, so my name is Jay Rosenberg, and I'm a senior security researcher on the global research and analysis team of Kaspersky, also known as GREAT. Formerly, I led the research at a startup called Intezer Labs, where we created a code reuse technology, and I've been reverse engineering and programming for about 14 years now. And I focus on threat intelligence, malware analysis, and reverse engineering. Okay, so just a quick overview. A couple basic things with Yara that just a little introduction. The next part will be building and managing data sets. Now, data is really important when it comes to building proper Yara rules that work. The next part will be going into using Yara for threat hunting, because you can use it in multiple ways, like if you want to detect something, and you build the Yara rule differently if you're actually hunting for new threats. Then I'll be speaking about building string rules, using unique strings from the binary, and then building rules from the actual code. And then I'm going to do like a case study with APT15's malware, Mirage, and show you how to build a rule with that. So Yara basics. So this is just like the basic syntax for a Yara rule on the top, and just demonstrating like a C-style comment. You see you have like the rule, the name, you can add some comments, some metadata, and a condition. Now, the metadata is actually really important because you don't know where your rule is going, and if you don't add comments and metadata, someone else who picks up your rule might not know what it's used for. So it's always good to add some information to your rule. And this clicker is not working. So one of the main modules that you can use with Yara is the PE module. Now this allows you to read information from the PE header. This is the most commonly used library that I use. They have one for ELF if you're more of a Linux person. Now you see like first it's checking for the header, the MZ header, by looking at the first 2 bytes of the file, 5A4D, and then it's checking if the file is exporting get module handle A, and then it checks the number of sections. And if it has 3 sections and all these conditions are met, then you have a valid match. So, as I said before, building and managing these data sets is very important in creating successful rules. The more data you have, the better. So there's a few essential data collections that I believe you should have. One of them being a small, clean collection. Now these are files that you know are clean. You don't want this collection to be too big, because when you're testing your rules, if you make the collection too big, then it might take a long time to run the Yara rule. And you don't want to run a Yara rule over a large collection if you're going to have a lot of false positives. So you want to do this first with a small clean collection, check it against that, and make sure you don't have any false positives. The next collection that you want to have is a large clean collection. Now this, if you pass the first step with the small clean collection, now's the time to run it over a larger sample set of more clean files. And if you pass this, then you want to search it over files that you know are classified as malicious. Usually when you do this, you want to categorize them into families, like maybe say you have some Lazarus malware, or you have some maybe T15 malware, or Turla, whatever it is, and categorize them. And or if you just have a bunch of files you know are malicious, you can add them to their just unknown. And the last collection you want to have is just random data, random files. The more data you have, the better. You might get, this is stuff you don't know whether it's clean or it's malicious. This is just a data set of random files that you might find connections that you didn't know existed before, and other malware to the same family or threat actor that you're looking to hunt for. So there's like a big problem when it comes to getting data. I come from a small startup in Tel Aviv, and our biggest struggle was getting data for when you're not like such a large company. So there's a few sources, the normal one is VirusTotal. I mean, this is pretty much all I had as a data source in order to find new APTs and new threats that maybe went undetected by other vendors. There's also VirusBay, which is ran by a colleague of mine, Ido Naor. It's a community of malware researchers that share samples. I'm sure we can arrange some invite codes after this. There is actually, Ido and Danny. Can you give out some invite codes after this for VirusBay? All right, cool. I put CNET up here, just like maybe that's where you're going to get some clean files, because as I said, clean files are just as important as malicious ones. Microsoft, maybe you take like a whole operating system, extract all the files, you know these files are clean, and this could be part of your clean data set. And then Malpedia is another one that you can also collect malware off of, a bit similar to VirusBay. So you need something to manage all this data. Now, before I joined Kaspersky, they gave me access to their system called Clara. Now, this is a Yara management system. You put up a bunch of collections that I talked about before, and then you're able to actually search Yara rules over these collections. And it's completely open source. You can find it on GitHub. And I was using this before I joined Kaspersky. I think it's the best platform for managing your data sets. So this is just an example of what it looks like when you search a rule via Clara. You see you have the status, finished, just the execution times. This is a rule. The collection it tried to search over was SAS, and it didn't match any files. But when you'd use this in your own case, you can create like your own collections. Like this was the collection SAS. Now you can create those 4 essential data sets that I was talking about earlier: the small clean, the large clean, the malicious, and the random data. So moving into threat hunting. As I said before, there's a difference between hunting for new threats versus using Yara to detect. So threat hunting, you want to make like what I call loose rules. This includes a lot of wildcards. So if a certain instruction, maybe the register is going to change, so you want a wildcard, the byte responsible for saying what register is there. The thing with this, though, is you have more false positives, but you have a higher chance of getting a new variant. I can tell you this from being at a startup, and the only thing I was able to search Yara rules over was VirusTotal. And I managed to find APTs, name the malware, and just by building these rules. The other thing you can use Yara for really is detection. But these are tight rules. These are rules meant to detect certain variants, and they're more specific. And that's maybe if you want to scan computers on your network and detect like a certain variant of a malware. So where can you use these Yara rules? As I mentioned before, as data sources, VirusTotal and Malpedia both let you search Yara rules, or you can upload a rule to VirusTotal, and every time something gets scanned, it scans with your Yara rule. Now, the way I build rules, I almost took VirusTotal down. I got an email from Victor, the creator of Yara. He wasn't too happy with me. He sent me a photo of a graph of when it ran against my rules, and their server CPU usage peaked. So try not to wildcard things too much, and it's not my fault if you take down VirusTotal. So just like a procedure for building these successful rules, first you want to do an analysis. So you take whatever malware samples you have access to that you're looking to find maybe new variants or other tools from the same group. So you want as many tools from the same group or the same malware family that you can analyze. The second step is to identify strings, code, maybe even metadata of the PE file or ELF file, whatever you're using Yara for, and find the unique information like the strings. The third step is actually build the rule using the information that you got from the binary. Four is to test it on those data sets that I spoke about before. You're going to go over with the small clean data set, the large clean data set, your malicious data set, and your random data. Now you want to deploy the rule. Now, at this point, maybe it passed all your tests. You don't have any false positives, but there's a lot of data out there on the internet. So maybe you put it up to VirusTotal, and you start getting a lot of false positives. This used to happen to me a lot because we didn't have much data. So you want to monitor the results that you're getting from if you're searching it on VirusTotal for like false positives, and maybe you have to adjust something in your rule. So this is, I want to show you the difference between string rules that tend to stop working after a couple generations of the same malware, and rules that are built off code. The thing about malware is like the strings might disappear, but they're still using the same code base. So this is just an example binary that I made, and we can see, okay, we have what can be a unique string, test space str, and we can build a Yara rule off of that. So this Yara rule is going to detect if a binary has this unique string, test str. But what happens here? This is often a common case in malware. Uh, they create the string as an array, and now searching test string will no longer work. So what do? Now, if you look at older samples, threat actors used to not do this type of thing, so you could just find the strings. As things have evolved, these techniques are to get around YARA rules, AV engines, and other security products. So if we look here, on the left we have the string in plain text, and then on the right we have it initialized as an array. But what stays the same, or almost the same, is the code. So I like to build my rules from the code, because the code doesn't change most of the time. So I'm going to show you it's demo time, so something's bound to go wrong. Sure. To what? What? Ito loves busting my balls. I'm his second wife, by the way. 10. Great question, Mo. Okay. Let's show the bytes. So here, if we look at the code, we can see after the string is initialized by an array here, we have a lot of the same code compared to the binary on the right. Now, it's not identical. If you actually look here, you see this one shows move ECX, which is going to give you different opcodes. Well, the same opcode, but for the register, the second byte that tells what the register is going to change. So on the right, you have move EAX. So now we got to build a rule that's going to work across both binaries from the code. So what we do here, let's just So in order to build the rule of the code, we want to be aware of things that can change from binary to binary. Maybe maybe the author used different compilation flags, maybe just a different compiler in general. and it just changed the code slightly, and we want these rules to work throughout multiple generations. So let's start building a rule over here. So I'm going to start from this code, which looks the same on both sides. So I'll go C7, 4, 5. See, the FC is the EBP plus var4, so that's going to change. So now we want to wildcard that. Anything like that that can change, maybe if they change the function slightly, it would be F8. This is something that we wildcard. By wildcard, I mean putting these question marks, which basically means it will accept any byte to match when you're matching this rule. Now, constants are a very good thing to look for. So we have leet as the constant here. So we're going to write that in the rule. We're going to do the same for the next line. Wildcard the offset for the EBP. Take the constant. Again, wildcard. Wildcard. Okay, so we covered those lines with the constants there. Now let's get to the next part. You see, this is where it changes. You have the move ECX here and the move EAX here. So what's going to happen is we're going to take the opcode for the move. Now it's 4D on the left, and on the right we have 4-5. So we're going to wildcard this because this is saying what register it's being moved into. So wildcard, next one's an offset from the EBP, so let's wildcard that. Now we have the same thing with these adds. On the left you have add ECX, on the right you have add EAX. So we're going to wildcard what says what register it's going into and the offset, and do that for all the adds, okay? So the next one, again, is still using the ECX. So we're going to wildcard the 4D and the F0. Same thing with the move. Going to wildcard here. Now, you see this XOR that we have. Now, this is a tricky one. When it's XOR EAX, it's actually a different opcode. So if you look over here, XOR EAX, you have the 8-1, and then the F2 specifying the register, and then the constant. If you look down here, when it's XORing the EAX, the opcode is 35. So how do we deal with that? That's different than just wildcarding. And you can see that it changes from binary to binary. The XOR EAX isn't down until here. The XOR EAX is the second one here. So we gotta be able to skip basically the opcode for this instruction because it can be different. Now the constants are the same, but the opcode is different. So if we continue building the rule, we want to do a bracket and 1 to 2. Now this 1 to 2 basically specifies that it's going to skip the next 1 to 2 bytes. This is because in one instruction the opcode is 2 bytes, and in the XOR EAX it's only 1 byte. So let's do the 1 to 2. Now let's fill in the constant, 999999. Here we go. For the move, doing the same thing as before for the move. And now here we're going to hit the next XOR. So we're going to do another 1 to 2. And then 1 1 1 1 1 1 1 1. 8, 9, doing the same thing for the moves as we did before. And then here's another XOR. So we're going to skip 1 to 2. And then we're going to put in the constant, bad food, in hex. Oops. Keep moving down. We have another move. Going to wildcard the same. Then we have some pushes with some constants. These are probably going to stay the same. Four, 1. So here we see we have a push EDX. This is another one that you wanna watch out for. You change the calling convention of a function, maybe from fast call or CDEC. The registers might change, or just the compiler you're using. So what I do for pushes is I do 5 and then a question mark. So basically this means anywhere in the OX50 and below OX60, it will accept anything in that range. As we can see on the right, it's push ECX, and on the left, it's push EDX. And then the last thing I'm going to add is just the opcode of the call, because it doesn't matter. This is a relative call, so the next 4 bytes can change because the distance might change from the call. So we'll just, instead of just adding the wildcard, we'll just take the rule as is here. So let's try and run this over both files. Where is it saved to? Save as. Okay. Now the first few lines is because I have the files open in IDA, and these are the associated files with IDA, so it's getting an error with those. But you see it caught sample 1 and sample 2. Both of these binaries, one is with the string that was initialized by an array, and the other binary is with the string in plain text. And now this was built from this rule that came from the code. Now the thing is, the code usually doesn't change. Threat actors, they operate just like software companies, and I'm sure a lot of you program or something like that. I tend to copy and paste code from project to project. I'm not going to rewrite the same function twice, and I'm sure many of you do the same. So this code, these little pieces of code, if you find the unique code, are what stands out. And this, if you put a rule like this up on VirusTotal, for example, let's say it was from an actual APT, you might find new variants, undetected variants, actual different malware, but from the same threat actor. And from my experience working at Intezer, when VirusTotal was my only option, this worked, and I was able to find new APTs all the time by building my Yara rules off the code. And just a quick quick demonstration with if we run it with just the test string, it only found the sample 2, which had the non-obfuscated string. So you can see that the code, by building it off the code, we find both binaries. Building it off the string, we only found one binary. And this tends to happen and Yara rules stop working. I noticed a lot of people online, they publish Yara rules, and it doesn't cover the code. And when it does, they take a unique function, but they don't wildcard things that can change, as you saw, like the registers, offsets, and these are things you need to take into account when building these rules. And as I said, don't wildcard too much unless you want an email from Victor, the creator of Yara. I heard I'm on a first-name basis in the VirusTotal office because of certain rules that I put up, and they had to disable them multiple times. And yeah, I'm not first-name basis, not on a good reason. Okay, so now I want to actually show. That was just a sample file that I compiled myself. So I want to show you with actual real-world samples. And I'm going to do that with the APT15 Mirage Fox, whatever you want to call it, and their malware toolset. So the way I used to, before I joined Kaspersky and I had the visibility that I do now, the way I used to build rules was I would go on different like security threat intelligence blogs, maybe SecureList or Palo Alto's Unit 42, ESET's blog, Checkpoint, any of them, and I would take the IOCs or even information that's in the post. Let's say there was a hash that was posted, but I can't find this hash anywhere. You can actually use data from screenshots or information from screenshots or other information that's given out in the post. So I'm just going to show you an example with a blog post that I did while I was at Intezer on Mirage Fox. You see we have like a code reuse from Mirage. At the time of finding this, there were only 10 detections on VT. So here's an example photo of some of the shared code. So what can you do here? Let's say you can't find the IOCs from the hashes on the bottom. You can take this information here and build a Yara rule actually from the code, just from a screenshot from a blog post. You can start writing from the opcodes. There's actually some unique strings here, and then maybe you can find other variants or the same malware but with a different hash, just from looking at one of these blog posts. Here's another example. Now this was a function for decrypting the CNC configuration, and I found this code to be in many of the APT15 and Mirage binaries. Now this is what I would consider a unique piece of code. Now the difference in the code here is you see it's checking the length 134 on the left, but on the right it's checking 12C. So what does that mean? It means we're going to have to wildcard this area of the code in order for it to work on other samples. So yes, this is how I work. Too many idle windows open. So let's take a Mirage sample. I mean, I just know where to find this function, but from like just the screenshot, you could actually build the rule if you took the opcodes. Just a little more difficult if you don't have the sample, because then you got to know the opcodes for each of the instructions. So here, let's get the opcodes. Now let's build a rule from this. Rule APT 15 condition C1. Okay, since we said that it looks like the only piece of code that's changing here is the length of the CNC configuration. So we're going to build the rule from the beginning of the function, 33C0, 0080. Now this is another thing that can change, is the address here. You have, maybe in this binary it's 10013268, and another binary it's different. So again, we're going to wildcard this. 4 bytes. And the INC now we have the 3D, and we're going to wildcard the length of the CNC configuration. 72 F2 C3. Okay. So now we built the rule from this CNC configuration decryption, as we saw in the blog post. That was unique code. Now what happens when I run this across the samples? Oops. So it looks like we got a hit. Again, this is the errors in the beginning are from the file being open in IDA, so you can ignore that. And it seems we got a hit with multiple Mirage samples, actually every one in the folder. And these different samples vary from, can go back to 2012 to something more recent in 2017. Whereas if you did it off the strings, these strings might have been obfuscated over the years to prevent detection. But still, the code hasn't changed, and we're able to build the rule based off this. Now, something interesting in here, this one. Now, this file that we actually hit, this is not a Mirage sample. This is another sample from APT15. Yet we took the unique code from a Mirage sample, and if we applied this like on VirusTotal, and we were waiting for a hit, it would have hit this file here, which is not Mirage at all, but it's another malware from the APT15 group. So you see, you can find, using the unique code instead of the strings, you'll actually find maybe other malware from the same threat actor because of the code reuse. As I said before, they tend to reuse code just like any software company would. I'm just showing you from the Shift F7. This is not how I reverse engineer. And if we look here, I mean, it's just an easier way to show that it's not the same malware. They're clearly different. So this is I built one rule from this unique code, and using this rule, we detected a different, brand new malware from the same group. This happens all the time. I'm used to having limited resources. Like I said, I was at a startup. We didn't exactly have a big budget or big visibility like I do at Kaspersky. So if you don't have large resources, and let's say you just have VirusTotal, this will still allow you to find new APTs or new threats without having access to so much data. So just to wrap up, as I've been saying, the thing you want to look for is code that is unique to specific samples. And you want to wildcard the things that can change from sample to sample. Not only this, you want to build those data collections that I mentioned before. You need a way to manage these data sets that you have, test the rules out, and make sure you're not popping up with a lot of false positives. There were plenty of times that I put up one of these rules. I thought, okay, search my clean collection, my small clean collection, search my large clean collection, search my malicious collection, and my random data, and then I put up on VirusTotal, and next thing you know, my whole email is getting spammed with false positive results, which means you need to adjust something. So the main thing is the code, it doesn't lie. The strings are easily manipulatable. So when building rules that you want them to last for generations and generations of different malware, and not only the same malware, but malware from the same threat actor, you should be using the code. Any questions? I believe they give out independent research accounts.
And when you upload it, you receive the results of who is other uploading files to your account, because other people, other users of the VirusTotal can't see them.
Well, what happens is you put the rule up. There's two ways you can do it. It's in the regular hunting, or you can do a retro hunt. A retro hunt lets you search the past 3 months of VirusTotal uploads with your YAR rule, and the other regular hunting, every time a file gets uploaded or rescanned in VirusTotal, it sends you an email, or you can check on their website with the results, the match essentially of the YAR rule, and the sample, the hash of the sample, which then you can go and download.
This information isn't shared among others.
The rule itself?
If you wrote the rule, only you will get the result.
Yes. That's correct.
You showed two samples, and you walked through, I don't know, like 10 commands or so. Like, was it like a function? How do you know, like, when you stop the YAR rule?
I mean, it can go on and on. You want to like basically it's something you pick up over time of doing this over and over again, and checking YAR rules that you've built in the past. Like, and if you keep practicing this, you start to see like what parts of the code that you want to build it off of. Now, right there in this piece of code, in the samples that I showed, there were some constants being used. Now, these constants tend not to change a lot, tend to use the same constant. So when there's a constant, this is an area of code that I'm going to look for and say, hey, I'm going to start writing the rule from here. I mean, there's other methods for this. You can.
And then can you take, like, for example, this YAR rule and other sets of YAR rules and compile them together with some master YARA and therefore catch like the entire operation? Is that
I mean, yeah, you can do that.
automate, like, or do I need to manually write everything?
Well, you could build something that automates it, that maybe wildcards, the things that I told you about wildcarding, I mean, I prefer to do them by hand, just because like of doing this for a long time and I can see exactly what I want. And sometimes when you build an automated tool, you know, it can add stuff that maybe it shouldn't have added, and I tend to do these by hand. But you can easily build a tool that takes, maybe you give it an address and an end address, and then it'll construct the rule itself using the wildcarding.
Success story with, you know, your manual Java writing, like one big group when you found like unique sample thanks to this?
Yeah, so actually, what I showed you before from the blog post on Integer, I found a low detection variant of Mirage. Here's actually the code reuse. Can't really see it. So there was 13% code reuse from Mirage. 74% of it was actually unique to this specific variant. And this is just one example of an APT that I was able to find while at a small startup just by using Yara rules that I was able to put up on VirusTotal. There's other examples of my old work on the Intezer blog. If you'd like to see more, I can show you later, Ido. In my room, yes. Naked. Any other questions? You may, Mo, yes. Anyone else want to watch? Pay-per-view, okay. That's a good idea. Let's make some money off it. All right, that's it. You can follow me on Twitter here at Jtezer. And thank you very much for attending.